Hello, I welcome you all in this presentation related with the subject failure analysis and prevention, and we are talking about the failures which are caused by the improper manufacturing. We have talked about the general aspects related with the causes which lead to the failure of the components manufactured due to the inappropriate manufacturing. So, there are various general causes and there are specific causes related with the each process. So, the general causes we have already talked, like the welding the procedure manufacturing procedure has not been properly established, or it has been it has been modified inappropriately without giving proper thought for its effect on the performance of the products which will be manufactured, or there is an non clarity and ambiguity or incomplete specifications are there in manufacturing procedure, or the procedure is not followed properly due to the inability to follow the procedure, like the system is not available, or system capacity is not available, or materials are not available, and then some inadvertent errors are made by the operators, or some accidental changes which are taking place in course of the manufacturing. So, those are the general causes which can lead to the deficient manufacturing, and deficient manufacturing promotes the deficiency, discontinuities and defects in the manufactured product, reduced mechanical performance, and increased sensitivity for crack nucleation and growth, which can cause the premature failure. So, now we will be talking about the specific issues or the specific ways by which the failures can occur, like in the processes which are the melting based, like casting and welding, and then where the mechanical forces are involved, where shearing is taking place, like in machining, and then the deformation based processes like rolling and the forging. So, rolling, forging, etc. So, inappropriate conditions can also lead to the defects in various categories. We know that whenever any metal is heated to the molten state, it becomes sensitive, it shows lot of affinity towards the atmospheric gases or the gases present all around. So, these gases, atmospheric gases interact with the metal. So, metal with the gases interact and forms the slag, and sometimes the slag is taken care of by using flux, but if it is not properly removed, then it leads to the presence of inclusions. In slag inclusions, flux inclusions, etc. can be there. It can also lead to the presence of the pores. So, this is what about the metal and the gas interactions, and this tendency becomes too high at a higher temperature. Another thing which happens in case of the casting is the alloy segregation tendency. You know that most of the metals are used in alloy form, so that because they have good strength. So, but whenever they are brought to the molten state, due to the various regions, it tends to segregate. So, alloy segregation tendency leads to the lot of metallurgical variations in the different zones, metallurgical variations. Then there is a variation in terms of the mechanical properties, increased galvanic cell formation tendency, so increased corrosion tendency. So, all these the things are promoted, and increased presence of alloying elements and absence of the alloying elements at other locations also promotes the hot tearing or the solidification, cracking in the weld or in the casting. So, these are some of the undesirable features which are caused by the alloy segregation. Then we have in castings, we can have the non-uniform cooling. So, at the surface metal is cooled rapidly as compared to the inner portions. So, so rapid cooling leads to the higher like say in the casting, if the molten metal comes in contact of the mold wall and transfers the heat quickly. So, the surface layer experience the higher cooling rate, and because of this very refined grain structure is produced. But if the metal is hardenable, then it can lead to the hard spot formation due to the high hardenability or hard microconstituent formation tendency. So, apart from the refinement, hard spots can also be formed if the metal is showing high hardenability due to the non-uniform cooling rate. We know that the core will be cooled at lower rates as compared to the surface zones, and this in turn brings lot of heterogeneity in terms of the grain structure and the properties. Unfavorable solidification pattern can also lead to the development of the crack, development of the defects. For example, if the solidification proceeds from all around, then the region last to solidify in this case will be present at the center, and when the liquid to solid state transformation at the center takes place, then it develops the shrinkage cavity at the center. So, piping defect and shrinkage cavities are the typical examples of the unfavorable solidification pattern, and therefore, it is always preferred that solidification proceeds from one side, like the heat is extracted in opposite direction and the solidification proceeds from one side to another in one direction. So, this kind of solidification is called directional solidification, and if it happens, then it will be reducing the shrinkage porosity formation, chances of the entrapment of the inclusions and the pores formation, and for that purpose only to have this directional solidification, only suitable chills, chaplets and the risers are used so that suitable temperature gradient can be established. So, the presence of these defects inside the cast components can be avoided, because if these are present, these will simply act as a source of the weakness and the stress concentration. Similarly, the residual stresses also develop in the castings due to the improper gating and rising design, and the development of the especially residual tensile stresses promote the cracking in form of say hot tearing, or it may be cold cracking after the solidification of the castings of the hardenable metals like steels and the cast iron. It is easy to recognize whether the product has been made by the casting or not. So, all the cast products will be showing the dendritic structure. So, this is a typical structure which is which shows somewhat poor mechanical properties as compared to the other products made by the other approaches. So, the cast structure is one typical feature which is observed in the casting. Apart from that, the castings comparatively show the poor hardness, strength, toughness and ductility, and there is also increased tendency of the defects in form of the inclusions, porosity, shrinkage, cavities in case of the casting, and invariably the alloying elements are ejected during the solidification into the liquid metal, and so the segregation is a very integral part of the castings, and which is also known as micro level segregation is termed as coring, while the macro scale segregation, if lot of things segregate at the center, then it promotes the hot tearing, and which is generally observed in terms of the increased presence of certain alloying elements at the center of the casting, or which will be increasing the tendency for the hot tearing, as well as will be having the difference in the structure and the properties of the casting. So, these are the some of the technical features related to the casting which promote the discontinuities and increases the tendency for defects as well as the reduction in mechanical properties in the cast component, and which frequently become the source of the failure in case of castings. This is one typical example wherein the inclusions and the pores are left within the inside the casting, while all around we can see the good dendritic structure, but there are some impurities and shrinkage pores which have not been filled in, and these discontinuities will be acting as a source of stress concentration which will be promoting the nucleation and growth of the crack. This is the typical, both these are showing the typical dendritic structure. This is the sound one, and this is where some discontinuities and defects are present in the casting. We know that for the welding there are three types of the approaches which are used, means for the joining purpose there are three types of the approaches which are used. One is where the edges of the components to be joined are brought to the molten state, means the fin surfaces are brought to the molten state like this, like the two components. So, edges will be brought to the molten state, and after solidification we will be getting the metallic continuity. So, basically it involves the partial melting which is coupled with the heat affected zone formation. So, base metal, HAZ formation and the weld metal. So, these are the three zones which are formed, will have the different structure and different properties which may, so the now weld may be stronger or weaker than the base metal, similarly HAZ may be stronger or weaker than the base metal. So, depending upon the type of metal and its a strengthening mechanism, a weld joint may be weaker or stronger than the base metal. So, we try to make efforts in such a way that at least joint can sustain the service load conditions, but if the process selection is improper, if the procedures are not followed properly, if the post weld heat treatments are not performed properly, then it will lead to the presence of lot of discontinuities in the weld joint, lot of weaknesses in the heat affected zone, and which will promote which will cause the premature failure of the weld joint. Similarly, there is another kind of another group of process where the components to be joined in the solid state without any fusion. So, in this case fusion is involved, we can say liquid state welding processes, and this is the solid state joining process where the mechanical deformation at the edges is achieved through the use of the force, so that the metallic continuity between the two is realized. So, depending upon the strengthening mechanism of the metal, this zone may be soft or this zone may be strong or hard. So, those metals which are work hardenable, they will be leading to the lot of increase in strength and hardness as compared to the precipitation hardenable alloys, which because of the deformation they get softened. So, the softening we can see in terms of the dip in term of dip in the hardness in the heat affected in the weld nugget zone, while in case when the hardening is taking place, so the weld nugget will be stronger. So, this is what you can say the variation in the hardness as a function of distance from the base metal across the weld joint. So, most of the like say 5000 series aluminum alloys and the steels show this kind of trend, while the 2000 and 6000 and 7000 series aluminum alloys show this kind of trend where the softening takes place, because these do not show appreciable hardening tendency. So, depending upon the metal systems, different metals show the different behavior under the influence of the external deformation caused by the external stresses, and that in turn may lead to the increase in strength and increase in hardness of the weld, or sometimes softening also. So, that is another category of the process. If the process parameters like the rotational speed, the forces which are being applied, the design of the tool which is being used, if they are not appropriate, then it can lead to the presence of number of discontinuities in the weld nugget, and which can act as a source of the weakness. So, sometimes despite of having the good metallurgical continuity, the joint may be weaker or stronger, and accordingly we need to see where from the joint will fail. Third category of the process is the solid liquid based process. Under this category we have brazing and shouldering kind of process, where both the components to be joined remain in the solid state. Only thing is that low melting point metal is brought in between the fin surfaces, which after the solidification gives the metallurgical continuity, but these joints become weak and not becomes strong enough. So, they cannot take high load or they cannot sustain the high temperature. So, these are good for reasonable or very moderate kind of the loading and moderate temperature conditions, say for just to have the joints for electronic circuits, such kind of the joints are used. So, as per the application we can use the different joints for the different purposes. So what I'm trying to say that there are different category of the processes, and each process results in the different kind of the structure and properties of the weld, as well as the zones next to the weld region, and which in turn affects the properties of the weld. And therefore, we need to see that our welding process, welding procedure is appropriate, so that at least the weld joint is metallurgically sound, mechanically, and it is free from the defect. At the same time, it has the required set of the properties, not just in the weld zone, but also in the heat affected zone. And for that purpose, sometimes it may be required to perform the post weld heat treatment, so that the properties can be restored and brought to the similar, brought as the properties can be brought at the same level as that of the base metal. So now we will be seeing that what happens, actually this is what I have already talked in case of the weld fusion weld fabrication. Partial melting is involved, and because of the partial melting, the edges are heated, and some of the, so the along the weld fusion line, the metal under the application of the heat will be expanding, and subsequently during the cooling it will try to contract. So this localized expansion and contraction leads to the tensile stress development. At the same time, it also causes the heat affected zone, and this combination of these two sometimes leads to the liquefaction cracking, especially the zone which is very next to the fusion boundary. What it is in this case, like say this is an alloy having the liquid to solidification temperature range, say from 1100 to 1000 degrees centigrade. So this is the boundary line which is corresponding to the 1100 degrees centigrade, and the line which is experiencing 1000 degrees centigrade is this one. In between these two we will have both solid as well as liquid. This is called as mushy zone, or the two phase zone, where both solid and liquid will be present. This zone becomes very thin. So in this case, some of the things will be in the solid state, some of the things will be in the liquid state. So the low melting point things will be brought to the molten state. So the liquid things will not be able to sustain the tensile stresses if they are being developed, and such kind of tensile stresses promote the cracking next to the fusion boundary. So the fusion boundary is this one, and the zones which are next to the fusion boundary, where both solid and liquid phases are present, there these zones under the presence of or in presence of the tensile residual stresses promote the cracking, which is called liquefaction cracking. Similarly, in fusion weld fabrication, like if the hydrogen is introduced in the weld metal, especially in case of the hardenable steels, this hydrogen gets into the heat affected zone, and if the heat affected zone, due to the high cooling rate, if it forms the martensite and high hardness, then it promotes the delayed cracking or hydrogen induced cracking. Hydrogen also causes like the porosity, and the presence of the atmospheric gases like the oxygen and nitrogen in the weld promotes the inclusion. So in the fusion welding, presence of these gases from atmosphere in form of oxygen, nitrogen and hydrogen promotes the inclusions force as well as delayed cracking, and all these will be acting as a source of weakness, source of stress concentration, which will be promoting easily on the nucleation and growth of crack to cause the premature failure under the influence of the external stresses. Now another thing, alloy element segregation also, like in the casting, alloying elements will be segregating at the center. We know that whenever there is a, like say this is the weld metal, and the solidification is proceeding from the fusion boundary towards the center, because heat is extracted in direction away from the base metal. So this solidification proceeds with the rejection of the alloying element in the liquid metal, and these alloying elements will be getting enriched into the liquid metal. So this is how the liquid alloying elements will be getting segregated at the weld center line. So here this weld center line has a lot of low melting point alloying elements, so which will be promoting to the solidification cracking, because presence of low melting point will be reducing the presence of high concentration of the alloying element, will be reducing the melting point of the molten metal, or reducing the solidification temperature of the molten metal, and which in turn will be increasing the tendency for the solidification cracking. And how does it happen? We will see this in this diagram. Say at the center line, if here we have lot of liquid metal yet to solidify, but at the same time some tensile stress is being set in due to the puff and due to the restraint from the sides, then these tensile stresses cause the suppression of the liquid under the influence of tensile stresses, and which will be leading to the formation of solidification crack. This is particularly formed along the weld center line, and this is primarily attributed to the segregation of the alloying elements at the weld center line. You know that the different zones in the fusion welding will be experiencing the different composition, will be experiencing different cooling rates, and due to the variation in cooling rate and compositions will be having the different microstructure, and the variation in microstructure in turn leads to the variation in mechanical properties. So, non-uniform structure and non-uniform mechanical properties are primarily attributed to the variation in composition as well as varying cooling rates which are experienced by the metal during the welding. You know that heat affected zone is the unique phenomena of the welding, wherein which is formed next to the weld zone, and it becomes very sensitive for cracking, especially in case of hardenable metals like steel and cast iron, and which may appear in form of the cold cracks and underbeat cracks. And wherever these cracks are present, they will be providing very high stress concentration, and high stress concentration will be promoting the crack nucleation and then their growth. Apart from the fusion welding process, what we will see when joining is carried out using the solid state joining processes, a lot of deformation these processes may be of the two categories. Solid state joining process, there are two category of the process. One where the macro scale deformation takes place, like friction welding, friction stir welding, or there is a micro level deformation like in ultrasonic welding, explosive welding, and there is a category of process where micro deformation plus diffusion is also involved, like the diffusion bonding. So, in these processes the kind of the discontinuities which are formed are of the different in nature, like in solid state joining process, if the two metals are being joined, if they do not mix, they do not metallurgically bond with each other, then it can form the interface which will be acting as a source of weakness, source of stress concentration. And this is what we can see, if the surfaces being joined have not been cleaned properly, then they will be present in form of then the impurities will be present in form of the inclusions, or if the deformation between the deformation and the flow of the metal which is coming from both the sides, means the flow of the metal which is coming from both the sides is not getting mixed properly, not forming good metallurgical bond, then due to the limited metallurgical bonding, there may be interface, or there may be suppression from that zone which can act as a source of weakness. Similarly, hard and soft zone is also formed as per the kind of metal system, as I have explained. Like some of the metal systems which due to the deformation always show higher hardness and strength in the weld nugget area, like the aluminum 5000 series aluminum alloys and the steels, because a lot of work hardening takes place in these systems, while on the other hand precipitation hardenable systems, they get softened due to the dissolution and reversion of the precipitates, because such kind of alloys get strength from the precipitates, and if these get dissolved, then the strength is reduced. So, hardening and softening in solid state joining can take place as per the kind of metal system which is present. Now, another process is the machining one, wherein we know that machining can be carried out by various approaches, and these approaches there are three category of the process for removing the material. One is mechanical one, basically we use shear stresses for removing the material like in all conventional machining. Then there is another category of process of thermal, where thermal energy is used. We may use laser beam or we may use electron beam or electron beam machining, or there may be plasma arc. So these are also, like the flame cutting is also used, the gas flame cutting is also used for preparation of the grooves in the metal systems. In all these cases, either melting is involved or ablation is involved for removing the material in very controlled way. But whenever it happens, we will be seeing that there is a heat affected zone formation, there is a ash cast layer at the surface which is being formed. Similarly, there is electric discharge machining also, where thermal energy is used for removing the material in very controlled way. In mechanical, like near surface layers will be having the deformed layer, which results in the hardening of the surface and improve the strength and the fatigue performance. Then there is a chemical based approach, where chemical interactions with controlled chemical interaction between the base metal and chemicals is used for controlled dissolution of the metals, so that the material can be removed in controlled way in order to have the desired size and shape. In this case, especially whenever material is removed by the chemical methods, there is no deformed layer like in conventional machining. So, there is no residual stresses or residual compressive stresses, and because of this we will find that the tensile strength and the fatigue strength of the components processed by the chemical methods are not that good as compared to that of the mechanical methods, where compressive residual stresses are present at the surface. So, what we can see here in thermal methods, we have a melting and ablation leading to the development of the recast layer, or means whatever portion, a part of the metal melted is removed, but a part of the metal melted is redeposited again, and then the heat affected zone is also formed. So, these things will be leading to a lot of metallurgical and mechanical heterogeneity, especially near the surface layer, and if such kind of components are processed are subjected to the fatigue loading or the high tensile loading, especially with the stress residues, then these promote the nucleation and the growth of crack, and which in turn promotes the premature failure of the component. This is one typical example wherein like the factors that will be leading to the failure in case of the machined surfaces. We know the machined surfaces will be having a lot of feed marks, rough marks. So, these feed and rough marks will be acting as a source of stress concentration, which in turn promotes the nucleation and growth of crack easily. Similarly, in the grinding processes, like in grinding, if the lot of heat is generated and under the effect of the coolant, if the hardened steel surface if the hardenable steel surface gets hardened, then it leads to the formation of the hard spot. Such hard spots will have the tendency for easy formation of the cracks and nucleation. It can also lead to the softening due to the localized heating and dissolution of the precipitates. Similarly, in case of the machining, all those machined surfaces wherein thermal energy is used for removing the material, a cast layer is produced with the cracks, especially in case of the hardenable steels, which reduces the fatigue and tensile strength. This is what we can see. If the component is processed using thermal energy based approach, then this is the bulk material, then there is a region which is affected by the heat, and the one layer which is present at the top. This is a schematic diagram showing the top layer as a cast layer or as a recast layer, and this entire zone can be termed as the zone which is affected by the heat, and below that we have the bulk material. And for actual system, what we can see here, these three zones can be seen from the different shades. The top layer is white, so we can say it is a white layer, although it is a recast layer or as cast layer. And then another zone is which is just affected by the heat, and third one is the bulk material. Now, coming to the deformation based manufacturing processes, we have the two broad category in the deformation based manufacturing process. One is hot and another is cold deformation. We know that the two processes work on the different principles. Strength in case of the hot deformation based processes is obtained through the grain refinement, and in case of cold deformation, strength is achieved through the work hardening. So, these are the two different approaches by which the hot deformed or cold deformed metals will have the different strength from the different mechanisms. And since the deformation is not uniform, especially under the cold working conditions, the deformation is more at the surface and less at the core portion. So, that in turn leads to the non-uniform deformation, and so non-uniformity in the mechanical properties. And that is why, apart from this, we will also be seeing that in case of the deformed components, whether it is hot and cold working, normally we have the annealed, in annealed metals we have equaxed grain structure, but after the deformation, what we can see when the thickness is reduced, all these grains get elongated in the direction of the deformation, whether it is rolling or the extrusion. So, this the controlled deformation of the grain in one particular deformation leads to the higher strength in direction of the grain flow as compared to the direction perpendicular to that. So, this direction in which the grains will be flowing is termed as the longitudinal direction, and perpendicular to that will be termed as transverse direction. So, in general, metals show the greater strength in the longitudinal direction as compared to the transverse direction. So, this is what we can see, there is variation in the structure in terms of the direction, which in turn leads to the variation in mechanical properties. Similarly, the surface layers at the surface layers in the component are subjected to the greater deformation as compared to the inner portion, and that in turn also lead to a lot of variation in mechanical properties. Apart from this, cold deformation especially decreases the ductility and which in turn increases the cracking tendency. Similarly, the limited localized flow increases if this is the kind of situation due to the improper control of the temperature, improper plastic deformation ability of the metal, inappropriate ductility of the metal, then the limited plastic flow can lead to the defects, presence of defects like laps and seams in the components being made by the deformation based processes, and which can become as a source of the weakness, source of stress concentration, and so these can promote the premature failure. Then bended structure is another one where one typical face is present in very localized way in the direction of the rolling, or unfavorable grain flow is present. Both these factors, bended structure as well as unfavorable grain flow with respect to the externally applied load direction leads to the weakness. Sometimes this increases the notch sensitivity, promotes the nucleation and growth of crack from such locations, and that in turn can become the source of, can be the source of the weakness, source of failure in case of the deformed component. Now, the failures in deformation based processes can occur due to the variety of the regions, variety of the features which are imparted to the product during the manufacturing by the deformation based processes. Like if the product is produced by the cold working or the cold deformation based processes, then the fracture can occur due to the limited toughness or the poor toughness, due to the increased sensitivity, increased surface cracking. Surface cracking especially happens when the material is having the limited ductility, temperature or it is the extent of the reduction which is achieved in one pass is also too high, then excessive surface layer deformation can promote the surface cracking. Unfavorable grain flow pattern, because the metal is stronger in the longitudinal direction as compared to the transverse direction, and so it is always preferred that the loading is there in the direction of the grain flow or in the longitudinal direction. These factors in combination reduce the fatigue strength, reduce the corrosion resistance, and increases the tendency for the brittle fracture. Residual stress due to the localized differential deformation means the more deformation at the surface and less in the core and increased anisotropic mechanical properties, increased loss of the ductility, all these increase the tendency for the failure, especially in case of the cold deformation based processes. And another undesirable feature is also for, especially for the steels which are produced if by the cold forming or cold working based processes, then it will be leading to the reduction in the ductile to brittle transition temperature. So, those components which are to be used under the low temperature conditions, it must be kept in mind that their ductile to brittle transition temperature is within the safe limit, as the cold deformed component, cold worked component can fail due to the high ductile to brittle transition temperature. Now we will see hot forming or hot working does not cause much of the problem related with the cracking or related with the anisotropy, but these gain because these the products hot worked which are produced by hot working, they gain their strength from the controlled grain refinement. But apart from that, the component can since the component is to be heated to the high temperature for hot working, means that is above the recrystallization temperature of the metal. So, if the metal is heated to the high temperature, then it will have the tendency for oxidation. At the same time, due to the poor dimensional control is also observed, poor dimensional control is also observed in hot worked component, because whenever metal is hot worked, it will be expanding. So, material is subjected to the deformation according for a given size and shape at a high temperature when it is in expanded form, but subsequent cooling will be leading to the differential contraction when the system is cooled to the room temperature, because all sections will not be having the same volume, same length, same thicknesses. So, variation in dimensions, variation in section sizes and thicknesses will be leading to the different kind of the contraction. So, this aspect has to be controlled very properly, and inappropriate control can lead to the poor control over the dimensions, and due to the oxidation also we get the poor surface finish in case of the deformed component. So, here I will now summarize this presentation. In this presentation, basically I have talked about the specific the issues, specific discontinuities and defects which frequently lead to the failure of the component, especially which are produced by the casting, welding, machining and the deformation based processes. Thank you for your attention.